Welcome to part 2 for our second day on electric currents. So in this one, we're going to be looking at the alternating current, or AC current. You might have noticed in the example we did in the last video, it said that you were drawing power in AC. You technically had an alternating current running through that particular air conditioner. And we didn't do anything special for that. And I even addressed the fact that the AC portion was there in the question. So I want to talk about that a little bit today. So one thing I just want to say about AC current is this is going to be the only place that we end up using it in this class for the sake of time. Now you can go through, so all next week we're spending our time with direct currents. And so with that, there's some stuff that, we could look at, and we could do the similar type of analysis for an AC circuit. We're not going to be doing that because it starts getting a lot more complicated and you don't actually get that much more new information out of it. And so with that, what we're going to be doing is in this video, we're going to justify why we're not going to do that by saying, here's how you can treat them the same. So, I've mentioned AC current a couple of times. Let's actually figure out what that is. So let's, discuss the two types of current. So the first we're going to be looking at is the direct current. And this is what we're going to be spending a majority of our time in for this class. So direct current comes from something like a battery. So with a battery, it's going to have a almost continuous output until it dies. So if we looked at the current as a function of time, like we have in the graph over here, the current is going to be consistent. Yes, in real life, the battery would drop off, but we're going to be looking at a time where that doesn't happen. Or in reality, what we're doing is we have magic physics batteries that never go bad. So we have this direct current. Alternating currents, therefore, must be different somehow. So an alternating current is something like in an electric generator. There's more information in chapter 21 about alternating currents, but again, we're not going to get too far into that. So we'll kind of see what goes on with that. So now we have a new graph that has the current as a function of time. And it's going to oscillate or alternate back and forth between a positive and a negative maximum value. So as the current is given right now, it is a sine graph. So you're going to just alternate back and forth between these two values. So if we wanted to write the voltage as a function of time, we would be able to use this equation here. So again, because this isn't going to be our focus in a lot of this class, do not stress too much about some of this information you're going to be seeing. So here we have the voltage as a function of time. It's going to be equal to our peak potential. So this is the maximum value that we have for our potential, times sine of 2 pi f. So f is going to be our frequency. Here in the United States, that's going to be 60 hertz, multiplied by the time. So this is our equation for the potential as a function of time, where here we're referring to the potential as the voltage. If we don't have 2 pi f, we could have omega, which would be the angular frequency value. So that means that if our voltage is given by this equation, we can use Ohm's law to go through, and we could write out, instead of having voltage as a function of time, we can now have the current as a function of time, where the current is going to go back and forth between our peak current times sine of 2 pi f times time or omega times time. So either, depending on the question we would be looking at, would determine if we have the voltage or the current that we would need to look at. But basically, they are going to be, because they're both sine and the inside information is both sine, the current and the potential change together. So if one is at its positive peak, the other one is also at its positive peak. You can then go through and you can do the same type of thing for looking at power in an alternating current. So here we're using the same equation for power. So we have current squared times resistance. We can plug in our equation for current and we can square it. And basically it just means our power over time is going to be alternating. So here we have our graph. It's power as a function of time. Because we've squared our value, that means that we don't have anything negative. We always have a positive power value, just gonna be bigger. And what I want to focus on right now is this dashed line. So this dashed line is really important because it's going to tell us the average power inside of our alternating current. And so with this average power, it's going to help us go through and figure out how we can treat an alternating current mathematically the same way as a direct current. Because I don't know about you, but I don't want to sit there and have to plug in sine all the time. I don't want to, especially because we're going to probably be dealing with not very nice numbers. I don't want to have to deal with it. I want to get away from using the sine value. And so for that, I can instead use the average power squared, which turns out to be half of my peak current squared. So the average power can be calculated with either 1/2 peak current squared times our resistance, or 1/2 peak voltage squared divided by the resistance. So it's the same equations, but because we have an average value, should technically use 1/2. Well, you'll notice we didn't use 1/2 in the previous example. So there's still something missing in completely connecting the alternating current to a direct current. But before we get into that, we need to just reiterate that the average or mean value is important for calculating average power. So we want to kind of, like I said, continue developing what we're looking at. Because if we're only focusing really on using the peak potential or the peak current, maybe there's something we can do to help us out some. And for that, we need to use the root mean square. So some of you may have seen the root mean square previously. It just means you're taking the square root of the average square. So here we have our average current and our average voltage, and they're both squared. And their average value is just equal to 1/2 times their peak current squared or the peak voltage squared. This is just the definition for the average value that was important for calculating the average power. If I take the square root for both of our equations, so we're square rooting our average value, we get the root mean square, or the RMS value. And this is what's going to be important. I know mathematically it's not very pleasant to have to put the 0.07 in here. Sorry, the 0.707 in. It's not very fun. Sure, you can just plug in the square root too. It doesn't really matter. But it's the root mean square value that's important. And so we need to remember we are here because we care about something. And it's not just getting an A in this class. We're trying to figure out how to connect some stuff. So the RMS value is sometimes referred to as the effective value. So with the effective value, what that translates to me without, going into a lot of, nitty-gritty stuff is that that's actually the value I can use. So when you saw in the previous example, that was an effective value that was given. And if we have the effective value, we can just directly plug it in to the power equations. So instead of having to do 1/2 times our peak current squared, I could just plug in the root mean squared value. They're the same exact thing. It's just the effective value makes it so I can just use the equations as they were originally given. So it's going to make our lives a little bit simpler, especially since questions will be giving us effective values in situations. So let's go ahead and let's do an example. So this is number 51 from the back of the chapter. So we're given some pieces of information, and this is what you need to look out for. Is in an example, if it tells you explicitly if it is an RMS value. So this tells me that my potential is an RMS value and it's 660 volts. This tells me I can use it directly, right? I don't have to worry about taking a 1/2 or anything like that. I can just use it as it is. In some questions, it might use some slightly different terminology to tell you the same thing. If it tells you you need to calculate an RMS and then there's more questions, you know you're not going to be given, you're being given a peak value, not the RMS or the kind of nice numbers that you can just plug in directly. So be careful with terminology when you're going through and reading. And then we also have the power given as 1800 watts. So in part A, we are being asked to solve for the peak value. So solving for V0. So my peak value is going to be equal to the square root of 2 multiplied by V RMS. Because again, our relationship, so our peak value is okay. So our original relationship that we were given for information is we had 1/2. Let's look at it for current. 1/2 our peak current squared was equal to our current RMS squared. So we can rearrange this because, again, the similar equation happened for the potential. We could rearrange it to find the equation that I've written down here. All right, so we multiply both sides by 2 and then take the square root, and this is what we have. So we can now just simply plug in our numbers. We have the square root of 2 multiplied by our root mean square potential, which was given us 660 volts. And we can just plug that in, and we're going to get 933.38 volts, or our peak potential, because we're given 2 sig figs, is 930 volts. So it's not too bad having to go from a root mean squared value back to its peak voltage. So in part B, we're being asked to find the peak current. So in order to do that, we need to use our equation for power. So average power is equal to the RMS current and times the RMS potential. So rearranging, because I want the peak current, I need to solve for the root mean squared current first. Oops. So I have that plugged in. So I've just rearranged my equation. And now I can just plug in my numbers that were explicitly given to me in the question. So I have 1800 watts divided by 660 volts. And my root mean squared current is going to be 2.7272 repeating. So let's make that a 3 amps. I'm not done because I wanted to find the peak current. So that was my I naught value. So I need to take the square root of 2 and multiply it by my root mean squared value. So if I do this, I'm going to have the square root of 2 times 2.7273 amps. Taking that and plugging it in, I got 3.8569 amps, or my peak current is 3.9 amps. So a lot of just this introduction to our alternating current has been to find this root mean square value, because now we can ignore the fluctuations in our values of current and voltage. And that means that we're going to be able to treat this alternating current, even though it's going to go back and forth between 3.9 amps. Right? It's going to go to positive and negative 3.9 amps. I can say, well, instead, I can pretend that my current throughout the wire is consistently 2.7 amps. So all of this is just so we can pretend that an alternating current is like a direct current. So when we build more into circuits for the next week during lecture, we're going to see how direct currents work. But if we use the RMS values of alternating currents, some of what we do is going to be similar. We'll find out later how different some of that can be, but for right now, for power calculations, we can treat our alternating and direct the same as long as we use root mean squared values. All right, make sure to watch the third video, which has to do with the nervous system and electricity.